Welcome to another deep dive, everyone. Today, we're going to be tackling decision trees.
All right.
But we're not just going to be talking about the theory.
Right.
We also want to understand why they matter in the real world.
Yes.
So think of it like this. You're prepping for a big meeting about machine learning, right?
Okay.
And you need to really impress everyone with your insights.
Mm.
And you want them to see that you really get it.
I like it.
So to do this deep dive, we've got some great sources lined up.
Yeah.
A really fascinating mix of academic lecture notes,
Okay.
and then also some practical advice from some real machine learning experts.
Cool.
So it's kind of like we're getting the best of both worlds.
Yeah, I like that.
So to start off with, we're going to be exploring the core concepts first.
Okay.
So we're laying that foundation, and then we're going to...
build on that.
Yeah, build on that, exactly.
Right.
And we're going to see how these trees are actually grown.
Okay.
And then finally, we're going to move on to that fascinating part.
Oh, yeah.
The forests that are built from these trees.
Mm-hmm. I'm excited for that.
Okay, so first things first.
Mm-hmm.
What is a decision tree?
Right.
Our sources describe it as a choose-your-own-adventure,
Okay.
but for data.
Oh, that's a good analogy.
Yeah, so you can think of it.
Hmm.
You start at the stump,
Okay.
that's the root node,
Right.
and each decision, it branches out from there.
I see.
And that leads you down a specific path
Okay.
until eventually you land on a leaf.
Right.
And the leaf is a terminal node,
Okay.
and that's what gives you your answer or your prediction.
That makes sense.
Okay, so it's kind of like a flow chart.
Yeah.
But how do we actually decide
Hmm.
which branches to create?
That's a good question.
Yeah, because, I mean,
Hmm.
you don't just randomly split the data.
Right. It's not just random.
Right.
It's about finding,
It's got to be.
the best split at each step.
Yeah.
And to do that, we use something called information gain.
Information gain.
Yeah.
Okay. That sounds intriguing.
It is.
Can you kind of break that down for us?
Absolutely.
What does that mean?
Okay, so imagine you're trying to predict if someone will play tennis
Okay.
based on the weather.
Okay.
So you have data on the outlook, whether it's sunny, overcast, or rainy.
Right.
You have the humidity and you have the wind.
Okay.
Which of those factors do you think gives you the most useful information for your prediction?
I'd probably say outlook
Okay.
because, whether it's sunny or overcast or rainy, seems like it'd have the biggest impact
Exact.
on whether someone wants to go and play tennis or not.
Yeah, and that's exactly what the decision tree algorithm is trying to figure out.
I see.
Which attribute,
Oh.
like the humidity or the wind, gives us the most information gain.
Got it.
And it does this by measuring something called entropy.
Entropy. Okay, I've heard of that term before, but I'm not really sure,
Sure.
what it means exactly.
So entropy is basically a measure of uncertainty
Okay.
or randomness in the data.
Okay.
So a high entropy means our data is kind of all over the place,
Mhm.
and it's hard to make predictions from it.
Okay.
But a low entropy means things are more organized
All right.
and predictable.
I see. So if we split our data based on the outlook
Yeah.
and we suddenly see this big drop in entropy,
Right.
that means we've made a good split.
Exactly. That's exactly what information gain measures.
Okay.
It measures how much splitting on a particular attribute reduces the entropy.
So it's reducing the uncertainty.
Yes, reducing the uncertainty in the data.
Okay.
It's kind of like finding the perfect dividing line to separate our data points
Right.
into the most predictable groups possible.
Okay. So it's all about maximizing information gain at each step.
Exactly.
But I have a feeling it can't be that simple.
You're right.
There got to be some challenges along the way, right?
Sure.
What are some of those challenges?
So one challenge is that sometimes our decision trees become a little too good
Okay.
at fitting the data they're trained on.
Okay.
It's like they're memorizing the answers instead of actually learning the underlying pattern.
Mm-hmm. Yeah. We call this overfitting.
Overfitting. So it's like that student who aces the practice test,
Yes.
but then completely bombs on the real exam
Exactly.
because they didn't really understand the material. They just memorized it.
Yeah, that's a great analogy.
Yeah.
And just like we need to teach students to generalize their knowledge, we need to prevent decision trees from becoming too specialized
Okay.
to their training data.
So how do we do that?
Right.
How do we tame these overachieving trees?
So one solution that one of our sources mentioned is pruning.
Pruning. Okay.
Yeah, it's like trimming a bonsai tree.
Okay.
You carefully remove unnecessary branches to create a more balanced
Right.
and generalized structure.
So we're not letting it get too...
Exactly, big and unwieldy.
Yeah, we don't want it to be too rigid or specialized.
Right.
We want it to be adaptable.
Yeah, be able to handle new situations.
Exactly.
Okay. So that makes sense.
And this brings us to another important type of decision tree.
Okay.
Regression trees.
Regression trees. Okay.
So far, we've been talking about classification trees,
Right.
which predict categories.
Like yes or no.
Exactly, yes or no, will someone play tennis or not?
Wait.
But what if we want to predict something continuous?
Oh, okay.
Like
Sure.
the number of people who will play tennis.
Yeah, and our sources actually use that same tennis example.
Right.
But instead of predicting will they play tennis, yes or no, they focused on the number of players.
Exactly.
So that shows how versatile these decision trees can be.
Yeah, they are.
You can use it for all sorts of things.
So regression trees are built for predicting continuous values.
Okay.
So instead of maximizing information gain at each split,
Hmm.
they try to minimize the difference between the predicted values
Okay.
and the actual values.
So it's still about finding the best split.
Yes.
But with a different goal in mind this time.
Exactly.
Okay. So could you give us like a concrete example
Absolutely.
of how this works?
Okay, so imagine you're trying to predict
Okay.
how many ice cream cones a shop will sell. Right.
Depends on the temperature.
Okay, yeah.
So a regression tree might split the data based on temperature ranges.
Okay.
So like below 60 degrees,
Right.
60 to 70 degrees,
Mm-hmm.
70 to 80 degrees, and above 80 degrees.
Got it.
And for each temperature range, the tree would predict a specific number of ice cream cone sales
I see.
based on the average sales within that range.
Okay, so it's still about dividing the data
Yes.
in a way that leads to the most accurate predictions,
Mm-hmm.
but now we're predicting an actual number
Yeah.
instead of just a category.
Right.
Okay, so we've got classification trees for categories,
Yeah.
regression trees for continuous values.
That's right.
What's next?
Well, so far we've been talking about single trees,
Okay,
working in isolation.
right.
But what if we could combine the power of multiple decision trees?
Ooh. Yeah,
That's where things get really interesting.
I like where this is going.
We're going to explore ensemble methods.
Ensemble methods.
Yes,
Okay.
which are techniques for combining multiple decision trees.
Right.
To create even more powerful predictive models.
Okay, so it's like having a team of experts.
Yes, exactly.
All pooling their knowledge together
Mhm.
to come up with a more accurate
Right,
and robust prediction.
exactly.
Okay, now we're talking a whole team of decision trees.
Yeah.
That sounds impressive.
So are you ready to learn more about how these ensemble methods work?
Yes, I am, definitely.
Okay, great.
What kind of advantages do they offer?
We'll dive into that next.
Okay,
We'll explore the two main approaches, bagging and boosting.
bagging and boosting. Okay.
These techniques offer different ways to harness the collective wisdom of multiple decision trees,
All right.
and they've led to some remarkable breakthroughs in machine learning.
Okay. Well, I'm excited to hear all about it.
I'm excited to share it.
Ensemble methods, huh?
Yeah,
Multiple decision trees all working together.
that's right. I'm picturing like a team of data detectives,
I like that.
each with their own little unique perspective.
Yeah, so one of these ensemble methods is called bagging.
Bagging, okay.
Yeah, so imagine you have a data set
All right.
of 1,000 tennis matches.
Okay.
With bagging, you create multiple bags of data
Okay.
by randomly sampling 1,000 data points with replacement,
That's replacement. Okay.
which means that some matches might get picked multiple times,
Right.
and some might not get picked at all.
Okay, so each of these bags is kind of like
Yeah,
a slightly different version of the original data set.
exactly.
So what do we do with them?
So then we train a separate decision tree
Okay.
on each bag.
Right.
And since the data in each bag is slightly different,
Right.
the resulting trees will also be slightly different.
Interesting.
Yeah, they might prioritize different features
Okay.
or make slightly different splits,
Right.
giving us a diverse set of perspectives.
Yeah, I'm starting to see how this team of experts idea comes into play.
Yes,
They each have kind of their own little unique insights
exactly.
based on the data that they've been given. But how do we combine their predictions?
So for classification tasks, we just take a majority vote.
Oh, okay.
Whichever class label gets the most votes from the trees.
Okay.
That's the one that wins.
All right.
And for regression tasks, we average the predictions of all the trees.
So it's like a democratic vote among the trees
Exactly.
or a collective average of all their predictions.
Yeah, and it seems like this approach
Yeah.
would lead to a more stable
Yeah.
and robust prediction.
Because you're not just relying on one.
Exactly.
You're getting input from multiple sources.
And this brings us to a popular type of bagging algorithm called random forests.
The random forests, I've heard of that.
Yeah, so they take this idea of diversity a step further.
Oh, how do they do that?
By adding another layer of randomness.
Okay, another layer of randomness, all right.
So instead of considering all of the features, like the outlet, the humidity, and the wind, when making a split, a random forest randomly selects a subset of features at each split.
So it's like each tree only gets to look at a portion of the available information.
Exactly.
That sounds a little counterintuitive.
It does.
Wouldn't using all the features give us a more accurate prediction?
You might think so.
Yeah.
But forcing the trees to focus on different subsets of features actually helps reduce correlation between the trees.
Oh, okay.
Making their predictions more independent.
I see.
And this, in turn, leads to a more robust and accurate ensemble prediction.
Okay, so it's like that old saying, 2 heads are better than 1.
Exactly.
But in this case, it's like many diverse heads are better than 1.
Yes, I like that.
Okay, so we've covered bagging.
Right.
Which is all about creating diversity among the trees. But what about boosting?
Yeah.
That was another ensemble method that our sources mentioned.
Boosting is a different approach.
Okay.
Instead of training multiple trees independently, boosting builds trees sequentially.
Okay.
With each tree trying to correct the errors made by the previous trees.
So it's like a chain of mentors.
That's a great way to put it.
Each one learning from the mistakes of the last.
Yeah.
And passing on kind of their improved knowledge to the next.
Exactly.
Now, the source material mentioned AdaBoost.
Yes.
As a key example of this boosting technique.
AdaBoost is a classic boosting algorithm.
All right, so how does that work?
So it uses a clever weighting system to focus on the data points that are difficult to classify.
Right.
So each data point starts with equal weight.
Okay.
After the first tree is trained, the weights of the misclassified data points are increased.
I see.
This makes them more important for the next tree in the sequence.
So the next tree pays more attention to the data points that tripped up the previous tree.
That's a good way to put it.
So it's like each tree gets a chance to learn from the mistakes of its predecessors.
That's right.
And is making the ensemble progressively better over time.
Exactly. And this process continues. With each new tree trying to fix the errors of the previous trees, and the final prediction is then a weighted combination of the predictions of all the individual trees.
Right.
With more weight given to the trees that performed better.
So it's not just a simple average or majority vote anymore.
No.
The trees that have proven themselves to be more accurate get a bigger say in the final prediction.
Exactly.
This is really cool.
It is.
It's a fascinating way to combine the strengths of all these different models.
It really is. And the results speak for themselves.
Oh, yeah.
AdaBoost has been incredibly successful.
Wow.
In a wide range of applications.
Okay, so now remember that intriguing idea from the source material about combining AdaBoost with random forests.
Yes.
This is where things get even more interesting.
This is my favorite part.
Tell me more about this.
Okay, so imagine starting with a bunch of diverse decision trees.
Right.
Each trained on a random subset of the data and features, and then applying AdaBoost to iteratively refine them. Right. Focusing on the data points that are proving difficult to classify.
So you're taking the best of both worlds.
Yes.
And kind of merging them together.
Exactly, merging them into a single supercharged ensemble.
That's impressive.
It is.
That sounds like it could lead to some really remarkable...
It has advancements in machine learning.
It certainly has that potential. And, you know, this constant innovation is what makes this field so exciting.
Yeah.
Researchers are always looking for new ways to refine and combine existing techniques to really push the boundaries of what's possible.
It's amazing to see how these sophisticated algorithms are built on these relatively simple concepts.
Yeah, like entropy.
Right. Entropy, information gain.
And error minimization.
Yeah, and that's one of the things I think that makes decision trees so appealing.
I agree.
They're relatively easy to understand, even for someone who's not like a hardcore expert in machine learning.
Okay, so we've gone from single decision trees to these powerful ensembles.
We have.
But I have a feeling there's more to explore.
There is.
In the world of decision trees, right?
You're right. We've explored the how.
Okay.
But now it's time to delve into the why.
The why, all right.
Why are decision trees so valuable?
Okay.
And what role are they playing in shaping our world?
I like it.
So let's shift gears and explore some real-world applications and see the impact of decision trees in action.
All right. I'm ready. Okay, so we've covered a lot of ground.
Yeah.
From individual decision trees to these really powerful forests of them.
Yeah.
All working together.
It's amazing.
But now I'm curious, like, where do we actually see decision trees, like, making a difference in the real world?
Well, it's fascinating because as decision trees and these ensemble methods have become more advanced, they're being used in more and more important fields. We're talking about healthcare.
Wow.
Finance, even things like optimizing energy consumption.
Oh, wow.
Or predicting equipment failure in industrial settings.
So how about we pick one?
Sure.
And really dive in.
Okay.
I'm particularly interested in how they're used in healthcare.
Okay.
Our source material mentioned diagnosing diseases.
Right.
But could you give us like a more concrete example?
Absolutely.
Yeah.
So let's say doctors are trying to determine the best course of treatment.
Okay.
For a patient with a particular type of cancer.
Right.
They might use a decision tree model that's been trained on data from thousands of other patients.
Okay.
With similar diagnoses.
So this decision tree would have learned
Yeah.
like all the patterns in the data.
Exactly.
That link different patient characteristics, like their age, tumor size, genetic markers, treatment history.
To the success of different treatment options.
Okay.
Exactly. So the model can then help doctors determine which treatment is most likely to be successful.
Okay.
For a specific patient based on their individual profile.
So it's kind of like having this powerful tool that can just analyze these huge amounts of data and help guide medical decision making.
It really is incredible.
That's really amazing. It sounds like these decision trees have the potential to really personalize medicine.
I think so.
And improve patient outcomes.
Absolutely.
What about other fields like finance?
Okay.
How are decision trees being used there?
So imagine a financial institution is trying to assess the risk of a loan applicant defaulting.
Okay.
A decision tree model could be trained on data from past loan applications, looking at factors like income, credit history, debt-to-income ratio, and employment status.
Got it.
So the model could analyze an applicant's financial profile and predict the likelihood of them repaying the loan.
Okay, so it helps the institution make more informed lending decisions.
Exactly. It's all about using data to make more accurate and data-driven predictions, whether we're talking about medical treatments or financial decisions.
This has been a fascinating journey.
It has.
I feel like we've learned so much.
Me too.
We started with like the basic structure of a decision tree.
Right.
Then we explored how they're built.
Using all those?
Yeah, with concepts like entropy and information gain. And then we ventured into that powerful world of ensemble methods.
Those were fun.
Yeah. And then we saw how these algorithms are not just theoretical concepts. But they're actually being applied in the real world.
They are.
To make a real difference in these important areas like healthcare and finance.
Absolutely.
And so many other fields.
So many.
So for our listener out there, who's prepping for that big meeting on machine learning?
Right.
What are the key takeaways that you'd want them to remember?
Okay, so I'd say the most important takeaway is that decision trees, especially in their ensemble forms, like random forests and boosted trees, are incredibly powerful tools for making predictions and solving problems. They're relatively easy to understand. They can handle both categorical and continuous data. And they can be incredibly accurate. But it's also important to remember that they're just tools.
It's up to us to use them responsibly and ethically.
Absolutely.
And be mindful of the data we use. And the potential impact of the decisions that they help us make.
That's a good point.
So the future of machine learning is full of possibilities.
It is.
And understanding decision trees is a great starting point for anyone who wants to be a part of this exciting journey.
Absolutely.
Well said.
Yeah.
That's a wrap on our deep dive into decision trees.
That was fun.
Yeah. And hopefully our listeners feeling empowered to not only talk about them, but also see their potential impact on the world around us.
I think they're well equipped to handle that meeting now. And impress everyone with their insights.
All right. Well, until next time.
Yes.
Keep exploring, keep learning, and keep asking those insightful questions.
Absolutely.
Thanks for joining us on the Deep Dive.
Bye, everyone.